Good everyone. In today's session, we're going to do chemistry, specifically stoichiometry, which is also known as more concepts. So we're going to solve a question which was asked in 2017, 2017, that is pure chemistry, GCE. The question was, dilute to lead 4 oxide, that is the chemical formula, was added to 100 cubic centimeter of nitric acid solution, and 2 reagents reacted completely with each other, forming lead 4 oxide, that is the chemical formula, leads to nitrate and water. The equation is given below. So this was the equation: dilute lead to oxide reacting with nitric acid, giving lead 4 oxide plus lead 2 nitrate and water. So 13.70 gram of the lead 4 dilute to lead 4 oxide was used in the reaction. The question is, calculate the first question, the mass of the lead 2 nitrate formed in the reaction, the molarity of the nitric acid solution, and state with reason whether lead 4 oxide is basic oxide or not. So the question was carrying 6 marks. So what's the first thing? The first thing you need to do here is to write the chemical equation. So I'm going to say dilute to lead 4 oxide, which is a solid, is reacting with 4 molecules of nitric oxide. Nitric oxide is aqueous, producing lead 4 oxide, which is a solid, plus 2 leads to nitrate, which is all nitrate are soluble, so this should be aqueous, then plus water, of course, liquid. Okay, so I'm going to first calculate the number of moles of dilute to lead 4 oxide, then use those number of moles in order to calculate the number of moles of lead to nitrate by utilization of mole ratios. Okay, so since this compound which reacted was 13.70 gram, let me find the number of moles. So number of moles of dilute to lead 4 oxide will be equal to the mass of dilute to lead 4 oxide over the molar mass of dilute to lead 4 oxide. So the mass we've been given is 13.70 gram, which reacted. Now what is the molar mass? So to calculate the molar mass, I'm going to say this is dilute lead 4 oxide. So I'm going to multiply 4 atoms of oxygen times the mass of oxygen, at 16, and that should give 64. Then I'm going to say 3 atoms of lead multiplied by 207, giving 3 times 207, 621. Then I'm going to add 621 plus 64. So that is 621 plus 64. That is 685. So this is the relative molecular mass. So relative molecular mass is 685. So to find relative molecular mass, we just add the units. So we have 685, so it will be grams per mole. So that will be the relative molecular mass. So I'm going to say number of moles of lead dilute to lead for oxide will be equal to, so I'm going to say 13.70 divided by 685. So that is 0.02 moles. Okay, so we know now the number of moles. So to calculate the number of moles for lead to nitrate, I'm going to use the mole ratios. I'll say number of moles of lead to nitrate over the number of moles of dilute to lead 4 oxide. They are in the ratio of this one. We consider the stoichiometry coefficient. It is 2, there it is 1. So I'm going to say number of moles of lead to nitrate will be equal to 2, that is 2 into 1 into 2, that is just 2. 2 times the number of moles of dilute to lead 4 oxide. Okay, and this will give us 2 times the number of moles we found for dilute to lead 4 oxide, that is 0.02 moles. And once you multiply this, it will give us 0.04 moles. So these are the number of moles for lead to nitrate. Okay, now to find the mass, they asked about the mass of lead to nitrate in the reaction. So the mass, now we're going to say mass of lead to nitrate will be equal to number of moles of lead to nitrate multiplied by the molar mass for lead to nitrate. Okay, so I'll say the molar mass for lead to nitrate. I'll calculate first the relative molar mass. So we have lead, that can lead to nitrate. So I'll multiply this value, I'll distribute it by everything inside. So there it will be N2, 1 times 2, that is 2, that is 3 times 2, 6. So I'll say 6 by the mass number for oxygen, that is 16. Then we have 2 times the mass number for nitrogen, that is 14. Then I'll say 1 times the mass number for lead, that should give 207. So we have 207 there. We have 2 times 14, we have 28 there. 6 times 16, we have 96 there. So I'll say 96 plus 28 plus 207, that is 331. So this is the relative molecular mass for lead to nitrate. So I'll use it to calculate the mass. So I'll say mass now for lead to nitrate will be equal to the number of moles we found to be 0.04 moles multiplied by the molar mass, that is 331, which is 331. So the molar mass will be with units now, which is grams per mole. So this mole and that mole will cancel. So the mass for lead to nitrate will be equal to 0.04 multiplied by 331. So the mass is giving 13 13.24 grams. Okay, so that is basically the mass. So I'm just going to say mass for lead to nitrate will be equal to 13.24 grams. So you might be wondering why I used this value, why I used the number of moles for dilute 2 lead 4 oxide. The reason is very simple. It is because in this question they said the two reactants reacted completely, meaning that there was no excess reagent. If I thought there was an excess reagent, I would have used the number of moles for a limiting reagent in order to calculate the mass for lead to nitrate. Okay, all right, now let's so this was part A of the question. So let me now do part 2. Part 2 of the question is calculate the molarity of the nitric acid solution. So this will be part 2 of the working. Okay, I'm calculating now molarity. So the molarity has the formula. Molarity is simply the number of moles dissolved in a certain solvent. Okay, so molarity is just same as concentration, the amount of solid dissolved in a solvent. Yeah, basically 1 liter of the solvent. So I'm going to say molarity for, we are calculating for nitric acid, will be equal to the number of moles for nitric acid over the volume for nitric acid. So I'm going to determine first the number of moles from this nitric acid. So from our balanced equation, we can see that nitric acid, there are 4 molecules of nitric acid. So let me use the mole ratios. I'll use the mole ratios to determine the number of moles for nitric acid which reacted. So I'll say the number of moles for nitric acid which reacted over the number of moles for dilute lead 4 oxide are in the ratio of, we can see that there it is 4, and the stoichiometry coefficient there, it is just 1, meaning that the number of moles for nitric acid is simply 4 by the number of moles for dilute lead 4 oxide. Okay, so I'll say number of moles for nitric acid will be equal to 4 times the number of moles for dilute lead 4 oxide we calculated, and that gave us 0.02. So I'm going to say this 4 times 0.02 moles. So the number of moles now for nitric acid will be equal to 4 by 0.02, and that is giving 0.08 moles of nitric acid. So this implies that 1 mole of dilute to lead 4 oxide was reacting with 4 moles of nitric acid. So we've now calculated the number of moles which reacted in this particular equation. There were 0.02 moles of dye to dilute to lead oxide. So they reacted with 0.08 moles of nitric acid. So let me now calculate the molarity. So molarity for nitric acid now will be equal to the number of moles for nitric acid, which is 0.08 moles, over the volume for nitric acid. From the equation, we are told that it is 100 cubic centimeter of nitric acid, 100 cubic centimeter. Okay, so I'm going to convert that 100 cubic centimeter. So I'll just divide this value, which is 100. I'll just divide it by 1000. Okay, for me to convert it to cubic decimeters. So the volume should be in liters or cubic decimeters. Okay, so what value am I getting? So I'll just say 100 divided by 1000. It is 0.1, so this is 0.1 cubic decimeters. Okay, so that is the volume. Why am I doing this? I'm doing this because 1 cubic decimeter is basically equivalent to 1000 cubic centimeters. So you can just, if you want to find, since the volume which was given was 100 cubic centimeter, you can just put x there, then you cross multiply. So I'm going to find that x will be equal to 1 cubic decimeter multiplied by 100 cubic centimeter over 1000 cubic centimeter, and cubic centimeter will cancel, and x are going to remain with 100 divided by 1000, which is just 0.1. Then the unit to remain with the cubic decimeter. So this is basically what I did here by just dividing by 1000. That is the simplest way. So 0.08 divided by, and so I'm finding molarity to be, for nitric acid, to be 0.80 moles per cubic decimeter. So I'll just conclude as molarity for nitric acid is equal to 0.80 moles per cubic decimeters. So that is the molarity. Now let me find the last part of the question. They are saying, this is part 3. State. So the last part of the question was this one, which was state with reason whether lead 4 oxide is a basic oxide or not. Okay, so lead 4 oxide. Lead, I'm just stating. So lead 4 oxide is simply a basic oxide. Lead 4 oxide is a basic oxide. What is the reason to that? The reason is very simple. An oxide made up of a metal, or an oxide of a metal, is simply a lead 4 oxide. So the reason is because lead, because lead for oxide is an oxide of a metal. So all oxide of metals are simply basic oxide. Then when you're talking about acidic oxide are simply oxide of non-metals. Okay, oxide of non-metals are simply acidic oxide. For example, when you have carbon dioxide, when carbon dioxide is dissolved in water to form an acid, for example carbonic acid, so that is acidic. That's where the term acidic oxide comes about. So our lead for oxide is basically a basic oxide. Okay, so that's it for this question. Have a great day. Thank you for watching.